Massive cracks are opening across parts of Arizona, slicing through deserts, roads, farmland, and undeveloped land with little warning. Some stretch for miles across the landscape. Others appear as deep trenches capable of swallowing vehicles, damaging infrastructure, and altering entire sections of terrain. Why are these fractures appearing in one of America's fastest-growing states? Why do certain regions continue to develop new cracks while older ones keep expanding? And why are many of these openings growing larger even though they are not primarily caused by earthquakes? Across southern and central Arizona, the answer lies in a complex combination of geology, water use, and climate. The state has become one of the most fissure-prone regions in the United States, with hundreds of known ground cracks spread across multiple counties. Geologists continue to identify additional fissures each year, making it impossible to establish a permanent total. Existing fissures can lengthen, widen, merge with neighboring cracks, or become buried beneath sediment, only to reappear later through erosion. Current mapping by the Arizona Geological Survey shows approximately 169 to 175 miles, or roughly 272 to 282 kilometers, of confirmed earth fissures. Beyond those mapped features, another approximately 180 miles, or about 290 kilometers, of suspected or unconfirmed fissures have also been identified. The state contains approximately 26 to 27 major earth fissure study areas where the phenomenon is especially concentrated. Unlike dramatic tectonic ruptures associated with major earthquakes, most Arizona fissures form through a slower process that can unfold over decades. The cracks visible at the surface are often the final expression of changes occurring far below ground. Their appearance reflects a gradual transformation of the landscape driven largely by the removal of underground water. Arizona occupies a challenging environmental setting. Much of the state lies within arid and semi-arid regions where rainfall is limited and highly variable. Communities, farms, and industries frequently rely on groundwater stored within underground aquifers. These aquifers accumulated water over thousands of years as rain, snowmelt, and streamflow slowly filtered downward through layers of sediment. As population growth accelerated and agricultural development expanded, groundwater pumping increased dramatically. Wells were drilled deeper and pumping volumes rose across numerous basins. The process supplied water for growing cities, irrigated fields, industrial operations, and expanding economic activity. Yet removing large volumes of groundwater has consequences that are not immediately visible at the surface. Aquifers are not vast underground lakes. In many parts of Arizona, groundwater occupies tiny spaces between grains of sand, silt, clay, and gravel. When water is removed, the pressure supporting those sediments decreases. The grains begin to pack more tightly together, causing the sediment layers to compact. This compaction translates into a gradual lowering of the land surface known as land subsidence. In some Arizona basins, subsidence has reached several feet over recent decades. While subsidence itself can occur relatively uniformly across broad areas, the situation becomes more complicated when neighboring sections of land sink at different rates. One portion of a basin may compact rapidly because of intense groundwater withdrawal, while another section remains relatively stable. The difference creates tension within the ground. As the sinking area pulls away from the more stable area, the earth begins to stretch. Eventually, the stress exceeds the strength of the sediment near the surface, and a fissure opens. These fissures can initially appear as narrow cracks only inches wide. Over time, they may expand into much larger features. Rainwater flowing into the opening removes sediment from the sides and bottom. Repeated cycles of erosion gradually enlarge the fissure, transforming a small crack into a substantial trench. Arizona's geology makes the state especially vulnerable to this process. Much of southern and central Arizona lies within the Basin and Range Province, a vast geologic region extending across portions of the western United States and northern Mexico. For millions of years, the crust in this region has been slowly stretching. That stretching created the familiar pattern of mountain ranges separated by broad valleys. The mountains represent uplifted blocks of crust, while the valleys formed where sections of the crust subsided. Numerous faults developed during this long period of extension, creating zones of weakness throughout the region. Although most Arizona earth fissures are not direct earthquake ruptures, the pre-existing faults and structural weaknesses left behind by basin and range tectonics influence where fissures develop. Areas already characterized by buried fault zones or abrupt changes in subsurface geology often become locations where differential subsidence concentrates stress. The valleys themselves contribute another critical factor. Many Arizona basins contain thick accumulations of loose sediments deposited by ancient rivers, lakes, and alluvial fans. These deposits may include layers of sand, silt, clay, and gravel reaching hundreds or even thousands of feet in thickness. Unlike solid bedrock, these unconsolidated materials can compress significantly when groundwater levels decline. Clay-rich layers are particularly susceptible to compaction because water removal allows particles to move closer together. As a result, the sediment-filled basins experience much greater subsidence than the surrounding mountains composed largely of bedrock. This contrast creates ideal conditions for fissure formation. The compressible basin sediments sink, while adjacent areas remain comparatively stable. Stress accumulates near the boundaries between different materials, and fractures eventually emerge at the surface. The scale of some Arizona fissures illustrates the magnitude of the process. Certain fissures extend for as much as 2 miles, or approximately 3.2 kilometers. Visible openings can reach widths of 15 to 25 feet, or about 4.5 to 7.6 meters. Exposed sections may attain depths approaching 90 feet, or roughly 27 meters, although the full depth of many fissures remains difficult to measure because sediment and debris often obscure the bottom. One reason these cracks attract increasing attention is their ability to evolve long after initial formation. A newly developed fissure is rarely a finished feature. Instead, it becomes part of an ongoing cycle involving erosion, sediment transport, and continued subsidence. Arizona's annual monsoon season plays a major role in that evolution. During the summer months, intense thunderstorms can deliver large volumes of rainfall over short periods. Water rushing across dry landscapes seeks the lowest available pathways. Fissures provide ideal conduits. As runoff enters a fissure, it erodes loose sediment from the walls and floor. Material is carried deeper into the opening or transported underground through interconnected voids. The process enlarges the fissure and may cause sections of the surface near the edge to collapse. Repeated storms accelerate this widening. A crack that initially measured only a few feet across may become substantially larger after multiple monsoon seasons. In some locations, erosion transforms fissures into prominent landscape features visible from aerial imagery. The concentration of fissures is not uniform across Arizona. Several counties contain especially large numbers of mapped cracks due to a combination of groundwater use, basin geology, and historical subsidence patterns. Cochise County in southeastern Arizona contains some of the state's most extensive fissure systems. The Wilcox Basin has become one of the best-known examples of land subsidence and fissure development. Decades of groundwater extraction associated with agriculture have contributed to significant water level declines. As sediments compacted, numerous fissures formed across portions of the basin. Pinal County has also experienced widespread subsidence linked to agricultural groundwater use. Located between the rapidly growing metropolitan areas of Phoenix and Tucson, the county contains extensive agricultural lands that historically depended heavily on groundwater pumping. The resulting subsidence has generated multiple fissure zones. Maricopa County, home to the Phoenix metropolitan area, includes several regions where subsidence and fissuring have been documented. Urban growth, agricultural activity, and historical groundwater withdrawal have combined to alter groundwater conditions across parts of the county. Pima County, which includes Tucson and surrounding areas, contains additional fissure-prone basins. Groundwater development over many decades has contributed to subsidence in several locations, creating conditions favorable for crack formation. La Paz County in western Arizona has likewise experienced fissure development associated with groundwater withdrawal and basin subsidence. Although less densely populated than some other regions, The county contains geologic settings similar to those found elsewhere in the Basin and Range Province. The hazards associated with earth fissures extend beyond their visual appearance. A fissure crossing undeveloped desert may seem relatively harmless, yet these features can create significant challenges for transportation networks, utility systems, flood control structures, and agricultural operations. Roads built across fissure-prone terrain may experience cracking, uneven settlement, or structural damage. Pipelines crossing active fissure zones can be subjected to stress as the ground moves. Irrigation infrastructure may require modification or repair when subsidence alters drainage patterns. Property owners sometimes discover that fissures have appeared unexpectedly near buildings, fences, or access routes. Flooding represents another concern. During heavy rainfall events, fissures can redirect water flow into areas not previously vulnerable to flooding. Alternatively, concentrated runoff entering a fissure may accelerate erosion and trigger additional ground collapse along its margins. Despite these impacts, earth fissures often remain poorly understood outside the regions where they occur. One reason is that their formation generally lacks the sudden violence associated with earthquakes or landslides. The process unfolds gradually, sometimes over years or decades, making it less noticeable to the broader public. Confusion frequently arises regarding the relationship between fissures and earthquakes. The presence of a large crack naturally leads many observers to assume seismic activity is responsible. In Arizona, however, most mapped earth fissures are not earthquake cracks. Earthquake ruptures occur when accumulated tectonic stress causes movement along a fault. The displacement can produce visible fractures at the surface, but these are fundamentally different from subsidence-related fissures. Arizona fissures primarily result from groundwater depletion, sediment compaction, and differential settlement. That distinction does not mean tectonics are irrelevant. The Basin and Range Province remains an actively extended region, and Arizona contains numerous faults formed through millions of years of crustal stretching. Some fissures may develop along existing fault zones because those zones already represent areas of weakness. Nevertheless, groundwater-related subsidence remains the dominant factor behind most modern fissure formation. Technological advances have improved the ability to monitor these changes. Satellite-based measurements can detect subtle land surface movements across broad regions. Interferometric radar techniques reveal patterns of subsidence that might otherwise go unnoticed. High-resolution aerial surveys and geographic information systems allow scientists to map fissures with increasing precision. These tools have demonstrated that subsidence is often far more widespread than visible fissures alone would suggest. Large portions of certain basins may be sinking gradually, even where no obvious cracks are present. Fissures typically emerge only where subsidence differences become concentrated enough to fracture the surface. The long-term implications depend heavily on groundwater management and future water availability. Continued groundwater withdrawal can sustain subsidence and encourage further fissure growth. Even if pumping rates decline, some compaction effects may persist because compressed sediments often do not fully rebound when water levels recover. Arizona's water challenges add another layer of complexity. Population growth, agricultural demand, recurring drought, and pressure on surface water supplies have increased reliance on groundwater in various regions. Balancing those demands while minimizing subsidence remains a significant issue across parts of the state. Historical records show that many fissure-prone basins experienced substantial groundwater level declines during the 20th century. In some locations, declines measured hundreds of feet over time. Such changes altered underground pressure conditions enough to trigger widespread compaction. The resulting landscape changes are visible not only through fissures, but also through broad subsidence bowls, spanning many square miles. Within these areas, localized differences in sinking rates create the stresses that ultimately fracture the surface. Viewed from the air, some fissures resemble long scars stretching across otherwise flat terrain. Their paths often reflect hidden geological boundaries beneath the surface. In many cases, the visible crack marks the location where deeper subsurface deformation is concentrated. Not every fissure remains permanently exposed. Wind-blown sediment, erosion, Vegetation growth and human activity can partially conceal older cracks. Yet burial does not necessarily eliminate the underlying hazard. Heavy rainfall or continued subsidence may reactivate or reopen previously obscured fissures. The expanding inventory of mapped fissures demonstrates that Arizona's landscape remains dynamic. New cracks continue to appear in susceptible basins, while existing fissures evolve through erosion and continued ground movement. The exact number fluctuates because the phenomenon itself is ongoing. Taken together, the evidence reveals why Arizona stands apart from most states in the frequency and scale of earth fissure development. The region combines multiple ingredients rarely present in such a concentrated form: a naturally stretched crust shaped by basin and range tectonics, thick accumulations of compressible desert sediments, extensive groundwater extraction, and seasonal monsoon rains capable of rapidly enlarging existing cracks. The result is a landscape where the opening of a fissure is not an isolated event, but part of a broader geologic process. The cracks appearing across Arizona are visible reminders of changes occurring within the subsurface, where groundwater removal alters sediment structure and reshapes entire basins over time. Their continued growth reflects the interaction of geology, hydrology, and climate acting together across one of the driest regions in North America. Far from being mysterious ruptures appearing without explanation, Arizona's massive cracks are the surface expression of a long-running transformation. Hundreds of fissures already cross the state, totaling more than 170 miles, or more than 270 kilometers, of confirmed ground fractures. Additional suspected fissures extend for nearly the same distance again. As groundwater conditions continue to evolve and monsoon storms repeatedly reshape the terrain, Arizona's network of earth fissures remains an active and changing feature of the desert landscape, providing a striking example of how human water use and natural geology can combine to alter the face of the land itself. Yet one of the most important aspects of Arizona's fissure problem is that the visible crack is often only a small part of a much larger area undergoing change. A fissure may appear as a narrow opening at the surface, but the deformation responsible for creating it can extend across many square miles or many square kilometers. In some basins, the land is slowly lowering over broad regions, while only a few locations develop obvious fractures. This means the appearance of a fissure is often an indication that stress has become concentrated along a particular zone, rather than evidence that movement is occurring only at that exact spot. Mapping efforts over recent decades have revealed that fissures frequently form near the margins of subsiding basins where differences in settlement rates are greatest. One side of the landscape may be sinking more rapidly, while the adjacent area remains relatively stable. The resulting strain accumulates until the sediment can no longer accommodate the stretching, producing a break that eventually reaches the surface. Once established, that fracture can continue evolving, even if changes underground become slower. The challenge for land managers is that fissures do not always follow predictable straight lines. Some curve across the landscape, branch into multiple segments, or connect with neighboring cracks over time. Others remain dormant for years before renewed erosion exposes them again. As a result, maintaining accurate maps requires continual monitoring. Areas that appeared stable during one survey may reveal new fractures during the next. Transportation corridors illustrate the practical significance of this issue. Highways, rural roads, utility corridors, and drainage channels often cross the same desert basins where subsidence is occurring. Even modest ground movement can create maintenance concerns when it affects long stretches of infrastructure. Engineers must account not only for existing fissures, but also for the possibility that additional cracks could develop in the future as groundwater conditions continue to change. Agricultural regions face similar challenges. Much of Arizona's farming activity is concentrated within sediment-filled valleys, where groundwater has historically been available. These same valleys are among the locations most susceptible to subsidence. Changes in land elevation can influence irrigation efficiency, drainage patterns, and field management practices. In some locations, fissures have altered how water moves across the landscape during heavy rain events, requiring adjustments to infrastructure and land use planning. Climate variability may also influence future conditions. Extended dry periods can increase dependence on groundwater resources when surface water supplies become limited. Greater reliance on aquifers may contribute to additional declines in groundwater levels within certain basins. At the same time, intense rainfall events associated with seasonal storms can accelerate erosion along existing fissures, enlarging features that are already present. The combination creates a cycle in which underground changes promote crack formation, while surface processes continue widening those openings. Despite the scale of the phenomenon, Arizona's fissures remain fundamentally different from the dramatic tectonic ruptures commonly associated with major earthquakes. Their development is usually measured over years rather than seconds. The process is gradual, cumulative, and closely tied to the interaction between water and sediment. That distinction is crucial because it points directly to the mechanisms responsible for the state's expanding network of cracks. Across Arizona, the evidence continues to point in the same direction. Extensive groundwater withdrawal, naturally compressible basin sediments, long-standing structural weaknesses within the basin and range landscape, and powerful monsoon-driven erosion have combined to create one of the most fissure-prone environments in the United States. The cracks spreading across portions of the state are not isolated anomalies. They are the visible expression of ongoing geological adjustment, a process that continues to reshape Arizona's desert basins, one fracture at a time.